Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Happy to have Sanjeev Arora here. He's here still for the rest of this week and for all of next week, right?
Just this week.
Oh, just this week. This has been 4 weeks.
Yeah.
God, I shouldn't be taking the Lord's name in vain on this, should I? Anyway, I'm mumbling under my breath. So he will talk about geometry and expansion, a survey of recent results. And it's been great having him here for 4 weeks. It's just flown right by.
Thanks. So this is an evolving talk because this area continues to see more developments, and so the title changes too. Some of you may have seen earlier versions of this talk. And so at this point, it's a survey where I touch upon results from some of my papers and papers by other people. And what it's about is, in this first paper, we came up with a new approximation algorithm for an NP-hard problem related to graph expansion, and then it had applications to various geometric problems. So that's what I'm going to talk about. Okay, so here's one example of a problem that I'm talking about, SPARSEST CUT or edge expansion, where you're trying to cut a graph into 2 pieces. So you're trying to find a cut, S and S complement. And you're trying to minimize the interface, roughly. That's the feeling on all of these problems. So in this one specifically, what you're trying to do is minimize the number of edges in the cut divided by the size of the smaller set, the smaller side. Okay, so that's also called edge expansion. C-balance separator is a related version of this problem where you insist that each side of the cut contains a constant fraction of the vertices, a fraction C of the vertices. And okay, and the objective is the same. And this version suffices. So in general, these problems are used in divide and conquer type algorithms, and this is often good enough because it's giving you a cut where each side has only a constant fraction of the vertices, has at least a constant fraction of the vertices. Okay, so both are NP-hard, determining the best cut or the value of the cut even. And so in practice, you want approximation algorithms. So why are such problems important? In the theory of algorithms, they are important because they arise in all kinds of settings, such as analysis of random walks, PRAM simulation, packet routing, clustering, VLSI layout, etc. In all of these, somehow the problem is to cut a graph into 2 and you minimize the interface. And the 2 problems I mentioned and related problems are very natural for in those settings. These underlie many divide and conquer graph algorithms, in particular graph algorithms for some of those applications, but also others. And there's a very nice survey by David Schmois which surveys these. Mathematically, expansion is interesting because it's a discrete analog of isoperimetry and useful in Riemannian geometry because there's a classical result of Cheeger which connects expansion, or the continuous analog of expansion, to, was there a question? To the second value of the Laplacian. And finally, parameters such as expansion and so on and SPARSEST CUT are just graph theoretic parameters of inherent interest. So for instance, the Lipton charge and planar separator theorem and other theorems like that is an interesting branch of graph theory. So any new algorithms you come up with usually also give you some interesting graph theoretic insight into these parameters of inherent interest. So in this talk, or in the story that I'm going to tell you, there are 3 main characters. So the first was expansion, as I already said. The second is isoperimetry, which I said is a continuous analog of expansion. And by isoperimetry, let me just say, so the most classical result is, for instance, that in the plane, the object which of a given area which has a minimum perimeter is a circle. Okay, and there are analogs of that. So those are the kinds of theorems I mean by isoperimetry. So the circle is the object of a certain area which has a minimum perimeter, which is the minimum interface to the rest of the world. Okay. So isoperimetry is a continuous analog of expansion, and it plays a role in which I'll describe in a second. And so the third character here is geometry, and especially geometric embeddings of finite metric spaces. This is another interesting and burgeoning area of algorithm design, and you can design many algorithms by constructing geometric embeddings of finite metric spaces, and that plays an important role here. So these are all connected in this talk. And the bottom line is that I'll describe new square root log and approximation algorithms for various NP-hard problems, including the two I mentioned. And these are derived using geometric insights of this nature, and which in general, and which in particular have also led to new geometric theorems themselves, okay, with purely mathematical theorems, which will open problems in mathematics. Okay, so isoperimetry, is used as a tool in proving these theorems. Okay, so let me describe previous approximation algorithms for expansion problems. So they are the eigenvalue and spectral approaches, which originate in the work of Cheeger, which I already mentioned. And these go via a connection between expansion and eigenvalues, which has had tremendous influence in computer science in general. But as an approximation algorithm for expansion and for these other problems, it's not great at all, because it only gives a factor in approximation. Okay, so this is very useful in the context of study of expander graphs, where both parameters, expansion and eigenvalue gap, are constant. But for general graphs, the expansion is not. Yeah.
Factorial expansion. This is for the case of the approximation. These are where the cases that the cut is a constant size. What are the really hard instances?
Yeah. So maybe you can improve it to get root n or something. I don't know. By some kind of, I don't know.
But you are thinking of the hard cases as those in which the cut is, between n and n or log n. No, not here. What are the really hard instances?
So that we don't have any hard, as in like computationally hard, or?
Computationally hard, yeah. So what would you imagine are the hard instances where the cut is linear or constant?
Yeah, closer to linear.
Also to linear.
Yeah, but not quite.
Yeah, but then this gap is much better.
Yeah.
But you think of those as harder because this gap is...
No,
I don't know.
So we have now better inequalities, connecting other quantities, not just eigenvalues, to expansion, and those connections are much tighter, which I'll talk about in a couple of minutes. And for those, yeah, the interesting cases are where the graph is almost an expander. Okay, by the way, the bad example for this is just a cycle, the n cycle. Okay, and that'll come in one of the slides later on. Okay, so that's the oldest idea, which actually people still use in practice a lot, because many of the graphs in practice are like planar or something, and then these things work much better. Okay, so the next idea was due to Leighton and Rao about 17 years ago, which was a log and approximation. And it ushered in a new type of technique for designing approximation algorithms using LP duality and so on, multi-quantity flows, and this was applied to many other problems. But originally it was applied to expansion. And what this also led to was something of inherent graph theoretic interest. As I said, many of these algorithms lead to some interesting graph theoretic results. So it gave rise to approximate Maxwell-Min-Cut theorems, generalization of the classical Maxwell-Min-Cut theorem, and something called the region growing argument, which was used in many approximation algorithms. So that was the second technique. And then the third technique, which was related, was introduced by Linear London and Rabinovich, and soon after by Aumann and Rabbani. And that involved the observation that that cut problems have a very close connection to embeddings of finite metric spaces into L1. Okay, and I'll talk about this precise connection later on. But basically, the bottom line was that they showed that if you could come up with better embeddings, then you would get better algorithms. Okay, and so they reduced this problem of designing algorithms to a more mathematical problem of designing embeddings. And in particular, they were able to use a result of Bourgain about metric space embeddings to get a log and approximation, which was kind of like the latent Rao result. But it was a little bit more general, and it had some other applications. OK, so the new results are root log and approximation. So the best here was log n. The new results are root log and approximation. And for C-balanced separator, it's not quite a root log and approximation. It's a pseudo approximation. So if you're interested in finding a C-balanced separator, each side of the cut has at least C fraction of the vertices. Let's say C is 1/3. Then this will find a C prime balanced separator, meaning each side has, say, 1/10 of the vertices. Okay, so in most applications, that's still enough because each side of the cut has a constant fraction of the vertices. Okay, and the third result was a proof about the existence of expander flows in every graph. So what these are approximate certificates of expansion. Okay, and I'll talk more about that, but it gives a kind of structural insight into what is expansion and how it arises. Okay, and the bonus was that the disparate approaches from the previous slide, eigenvalue, embeddings, and the flow approach, all sort of got unified. You know, all played a role, and I'll talk about that also. Okay, so outline for the rest of the talk.
What are the other letters there?
Rao and Vazirani. Okay, so in the rest of the talk, I'll already start talking about graph partitioning problems, but okay, so I already said that. Then I'll describe this new approximation algorithm via semi-definite programming and how it's analyzed, just to give you a little idea. And that'll also introduce the fact that, you know, to analyze these algorithms and these algorithmic approaches, you need some difficult theorems in geometry, in high-dimensional geometry. And so I'll tell you about one particular such theorem, the structure theorem, what I call the structure theorem. And then this theorem and other theorems that people have derived from it have been used in geometric embeddings. And I'll survey the area of geometric embeddings, where there have been quite a few results lately. And I'll also then talk about expander flows, these certificates of expansion that I mentioned, because they've proved useful in designing faster approximation algorithms. Okay, something that doesn't use semi-definite programming, which is spoiled them all the time, but it's slow. Instead, these things are much faster. And then I'll give you an outline of how this result in high-dimensional geometry is proved, the structure theorem. And I'll finish with open problems.
So what's the best you can do in time n log n? So
What's the what?
in time O star of n?
What can you do?
Yes.
What kinds of things?
Yes.
So like things like sorting and...
No. For graph partitioning or expansion.
He's saying, what's the best that you, if he just gave you n log n time, what's the best?
I mean, you have an
that
n
you could
squared
do?
time algorithm for one approximation factor.
Okay, how about m log n? Because you need m, right? The graph has m vertices, m edges. M log n.
I'm fine.
So, okay, so we do have a heuristic. So Rao, Vazirani, and I have a heuristic, which actually they were able to analyze and show that it gives you log square approximation. But you know, for the square root log n, we don't know how to do it in m log n.
You do have some fast algorithms.
That's n squared, yeah.
That's n squared.
But he's asking m log n. And of course, some of the eigenvalue things may, like on planar graphs, constant degree graphs, sparse graphs, I don't know, may run faster too. Yeah. Okay, so that's what I'm doing next. I'm going to describe this new approximation algorithm via semi-definite programming and why geometry arises. Okay, and I'll start by describing what are called semi-definite relaxations for these problems. Okay, so remember the C-balanced separator problem is a problem where you're trying to find a cut where you're minimizing the ratio of the number of edges in the cut to the size of the smaller side of the cut. And you're insisting that each side of the cut contains at least a fraction c of the vertices. C is like 1/10 or 1/3 or some constant. Okay, so let's first think about writing an integer program, or actually even worse, it's a quadratic integer program, which will give an insight into how to write the semi-definite program. Okay, so the problem is just finding a cut can be thought of as assigning +1 or -1 to the vertices. So you're finding n values, +1 or -1. And I claim that you're doing this. You're trying to minimize this objective function subject to this constraint. And that's just because that's a cut, +1 and -1. And notice that for every pair ij, where I and j are on opposite sides of the cut, vi minus vj square over 4 is 1. And if they're on the same side of the cut, vi minus vj square is 0. Okay, so now you see that what you're minimizing is over all the edges in the graph, this quantity, because if they're across the cut, it contributes 1. If they're on the same side of the cut, it contributes 0. And you're saying that you want over all pairs I and j, the same quantity, to be at least c times 1 minus c times n squared. Yeah.
So have you removed the s from the denominator there?
Oh yeah. Oh sorry. This is only up to a constant factor. Sorry. Yeah. Yeah. So this quantity, is at least this, and could be at most n over n squared over 4. So yeah, there's some constant factor. Ignore it. So I'm interested in a root log and approximation. So Mike is pointing out that I have some slop here.
No, I think he wasn't asking about the constant. He was asking about the n squared. You want the magnitude of that is something n squared, and you're something between 0 and 1.
No, I think Mike was asking, this just corresponds to this. And then in the denominator, I have some number which is c times v, c times all the words, c times n, or n over 2, something in between there. And that's, up to a constant, just n over 2.
A constant and a multiple of n.
Yeah. So there's a multiple of All right. So this object will come up in future. What we're doing here is we are assigning distances to each pair, a distance between each pair of nodes, and the distance is +1 between when the nodes are on opposite sides and 0 on the same side. That's a metric because it satisfies triangle inequality. In particular, it's called the cut semi-metric. Okay, for every cut you can define such a metric. Okay, so these will come in later, so that's why I'm mentioning it here. Okay, so all right, so now we have this quadratic integer program. Of course, solving that is NP hard. So you find a relaxation, so that's the semi-definite relaxation we'll come up with. And instead of finding +1 and -1 assignment, you assign unit vectors to v1 to vn. And these are vectors in n dimensions, such that you're doing the same thing. Okay? So this is an idea of Lazzie's, actually, using semi-definite relaxations for combinatorial problems. Okay, and they can be solved, and these things can be solved in polynomial time. For instance, using the ellipsoid algorithm. That's the result of Grötschel-Lovász-Schreiber. Okay. So here's one more constraint you can add. So as we already noted, in the solution that we're looking for, these quantities, vi minus vj square, these satisfy the triangle inequality. So we can stipulate that the vectors we are finding also satisfy the triangle inequality in this sense. Okay, so that's the semi-definite program we're going to work with. And this semi-definite program had been identified 10 years ago, around the time of the seminal work of Gomans and Williamson, but it was just not understood how to analyze this thing. Okay, so what's new in the work with Rao and Vazirani is how to analyze it. Do you have a question?
Is there any intuition why adding the triangle inequality helps?
Yeah, so without the triangle inequality, this is actually very close to the eigenvalue relaxation. So that's no good. So you can come up with bad examples. Did I answer the question? Sorry?
This will give exactly a spectral factor.
Yeah. See, because without loss of generality, it will be a one-dimensional solution. The optimum solution will be one-dimensional, and then it's like that. Okay. So, did that answer your question? So that shows certainly that without the triune quality, this doesn't work. And then it was a question, and you could also easily show that once you add the triune quality, it's at least as good as latent Rao. So it's a log and approximation, and the question was whether it's any better. Okay. All right. So this I already said is a triune quality, and it's a funny kind of triune quality because, of course, without the squares, these things, these are Euclidean distances, so these satisfy triune quality. Okay. It's a norm, but the square of the Euclidean distance, the fact that it has to satisfy the triune quality, that's a real constraint. All right.
So this somehow forces the vectors to be more spread out?
Okay, so let me describe in the next slide, the incursion, how to visualize these spaces. Okay, so this is a geometric condition that you really have to focus on. Okay, and I'm trying to give you some insight into this constraint here. So this is what I call the unit L2 square space. So these are unit vectors, n unit vectors in d dimensions. So as I said, the SDP will give you actually n dimensions and n vectors in n dimensions. But just for notational, cleanliness, I'm separating out the d, which is the dimension, from the number of vectors. Okay. So yeah, the square distances satisfy triangle inequality. And what that means geometrically is that if you take any pair of points, the angle is subtend on the third is non-obtuse. Because if you think about this constraint with equality, that's, by Pythagoras corresponds to a right angle. Okay, so this being an inequality in this direction means that the angle is non-obtuse, meaning no more than 90 degrees. Okay.
So then I don't understand the intuition, because when you started in unit vectors in R.
In R.
And they had.
So that we don't know how to solve.
Because that had angles of 180
That's right.
degrees.
So we don't know how to impose that condition. If we did, then P would be equal to A.
Right, but why is it that why don't we do the opposite and require them to be obtuse? Because originally it was 180 degrees.
No, this is the angle. It's either 180 or 0. It's either 180 or 0.
Right. It's not the origin.
Right.
It's not from the origin. It's from the third.
Yeah.
Yeah, so there's no 3 points.
See, that would be still obtuse. I just should think of it as 3 points on a line and the middle point. So they all
Contribute.
Okay. And as I already pointed out, if you didn't have the squares, of course the triangle quality would be trivial, because we're talking about Euclidean distances. But asking that the square satisfy the triangle quality is a fairly strong constraint. Okay, and if you want to visualize what such points look like, think of the hypercube. Okay, so up to some scaling. So I define the space to contain unit vectors, and the hypercube I'm using is not consisting of unit vectors, but vectors of norm square root k. But still you can see. Okay, so apart from that technicality, if you think about the difference between two vectors and square it, well, it's just the sum of all the coordinates of the difference in this coordinate squared. But now the coordinates are +1, -1. So the difference is either 0, +2, or -2. So the square is just 2 times the absolute value of the difference. Okay, so it's just 2 times the L1 norm. So the square of the u minus v square is just twice, up to scaling, the same as the L1 norm. Okay, so, and this of course satisfies triangle equality. So therefore the square distances also satisfy triangle equality. And of course, geometrically also in a hypercube, you have the non-obtuse angle property. So That's another way to check it. So it's not a bad thing to think about a hypercube as a good example of an L2 square space. And in particular, what we'll see is that one of the main structure theorem that we'll prove is that every L2 square space, in some sense, in one aspect, is kind of like a hypercube.
So by imposing this condition, it seems you're forbidding something to be too low dimensional.
That's right. Oh yeah.
But then when you come back to Christian's question, that supposedly low dimensional is good.
So I think, at least in the case of one dimension, this constraint says that if you have -1 and 1 values, you don't have any values in between. So this sort of forbids you, of using like probabilistic solutions. You have to.
Using what solution?
Well, smeared out solutions. You have to pick, a side for each point. It makes you.
Okay. By the way, let me make a comment based on Ehud's question. So Ehud pointed out that these things are inherently high-dimensional, and I forgot to say that. So there's a classical theorem. It was an open problem by Erdős in the 50s, and it was solved 10 or 15 years later. It was, I think, a $500 or $1,000 problem. To prove that, if you have points like this, the maximum number of points you can have in d dimensions is 2 to the d. Okay, and so if d were 3, you could only have 8 points. Okay, so if you want n different points, you need log n dimensions at least. Okay, so these are inherently high-dimensional spaces. Okay, and that's why possibly it's kind of hard to visualize them.
So that's when you have the restriction that these unit vectors are distinct.
Yeah, n distinct.
That sort of clarifies some of these questions, because you started off with a one-dimensional example of n vectors, but they were all mostly not distinct.
Yeah. Okay. So,
and so is it hard to show that they could do the B?
So this book, proofs from the book? It's a very nice book, at least in that book. Yeah. Okay, so another fact is that L2 and L1 are subcases of L2 squared. Okay, so endpoints in L1 or with L2 or L1 distance, you can realize that as an L2 square space, with the same interpoint distances. So, therefore, if you prove a theorem about L2 squared, you are also proving a theorem about L1 and L2 and so on. So,
what exactly? What do you mean by subcases?
Okay, so take any endpoints and with L1 distance defined between them. Let's say choose 2 internode distances. You can realize that as an endpoint L2 square space.
How many dimensions?
That could be higher, yeah. Especially going from L2, you may need actually a continuum.
Well, the infinite sphere, of course, but it will be exponential, I think, in the number of points.
But yeah, if you want it exactly, yeah. Okay. All right. So that was the geometry of these things. Okay. So what we have is a new theorem about these spaces, and here's the theorem. So you have these n unit vectors in d dimensions, and let me say that 2 subsets of points S and T are delta separated if for every pair from S and T, every pair of points from S and T, the squared distance is at least delta. Okay, so what I've drawn here is a unit sphere, the points on the unit sphere, and S and T are delta separated if for every pair of points from S and T, the square distance is at least delta. So the theorem is that if the sum of all internode distances is omega n squared, in other words, the average distance between a pair of points is a constant. Remember, this is a unit sphere, so the maximum distance is whatever, √2 or something. No, sorry, is 2. So the maximum distance between any pair of points is 2. And what this is saying is that the average distance is a constant. Okay? Well, then there exists 2 Log sets S and T of size omega n, so a constant fraction of the vertices, that are delta separated, where delta is 1 over square root log n.
And this is tight
And this is tight for the hypercube, yeah. So the hypercube is a tight example for this. So you can't. There may be other ways to improve our overall result, but the structure theorem in particular is tight for the hypercube. Okay. All right. So.
Are these constants just omegas, or are they nice? Are they like 1, 2, 3?
They're not particularly nice. No, you lose the fair bit. Yeah, I don't think they're that horrendous, but I don't think they are half or something. Okay. Sorry?
Something like 600 or something, less than much.
Did you calculate it?
But just from the proof.
Okay. All right. All right, so there's a geometric view of this, which is the following. So you may have, many of you may have seen these geometric graphs, for instance, that arise in Borsuk's conjecture and so on. So let me say G sub delta is a graph in which ij is an edge if and only if vi minus vj squared is less than delta. Okay, so I'm connecting every pair of nodes where the square distance is less than delta. Okay. Then the alternative statement is that G sub delta is an expander if and only if delta is at most 1 over square root log n. Okay, so if you have an expander, this graph cannot be an expander if delta gets too large. Okay, it's not too hard. I mean, one direction is almost straightforward because if delta is too small, then did I get this right? Okay, anyway. Then there are two sets which are very far apart, so the graph is not expanded.
So this is a graph for the same set of vertices.
The same, yeah, it's the same hypothesis. Yeah. Okay, so it's one of these theorems about these geometric graphs, but it's about a very global property of the graph, namely whether or not it's expanded. Yeah.
The hypercube is an expander?
Yeah, because you're defining a new graph, right, where the edges correspond to. Yeah. I also didn't define what an expander is. It's for an appropriate notion. All right. Okay, so the main theorem immediately implies a square root log n approximation algorithm. And goes as follows. So remember we wrote down this semi-definite program, and I mentioned you can solve it in polynomial time, so you can get the optimum solution v1 through vn. And suppose the SDP value is this. Okay, I removed the constant 1 over 4 scaling factor. So it's just the sum of all the edges of vi minus vj squared. So this is the value of a semi-definite program, and I forgot to say this earlier, but it's obvious that this is a lower bound on the optimum. Remember, we have a minimization problem. So since you're relaxing it, all your integer solutions are still solutions. Therefore, what you might get, is no higher than the integer solution. So this is a lower bound on the value of the cut, of the best cut. And we're going to produce a cut whose value is at most square root log n times this value. Okay, so let S and T be these delta separated sets. I didn't say this, but there's actually a fast algorithm to produce these sets. So here's the algorithm to produce a cut. You do breadth first search from S. So you shrink S to a single point, and you do breadth first search. And breadth first search, I mean, with respect to this distance, vi minus vj squared, this function. Okay, so it's a weighted breadth first search, or shortest path. And you do breadth first search, and in this breadth first search, so let's have a picture. Okay, so you do breadth first search. Imagine sweeping, in breadth first search, the frontier, right? You're exploring more and more, and you sweep the frontier from S to T, and you stop when you reach T the first time. So now think of this as each of these frontiers of the breadth first search tree as a potential cut, right? All the vertices that are to the left of the frontier and to the right, and you look at all those cuts and you output the cut which has the fewest edges. Okay. And that's your output. Okay, so that's your cut. So why is that any good? Okay, so here's the analysis. It's basically one line. And let me show it over here. So here's the inequality that I'm claiming. So the point is, here's S. You're doing breadth first search from it. And here's an edge ij in the graph. Well, the breadth first search hits, think of it as a wave that's coming forward. It hits I, when, it's gone on, the breadth first search has gone on for this much distance from I to S.
You might want to take a different marker.
It's not visible, or?
Not very.
Semi-visible.
Yeah. Okay, so here's I, and here's J. It's an edge in the graph. And think of this as a wave that's coming forward. It hits I at the time when, this corresponds to, breadth first search corresponds to the distance, di of S. Okay, the distance of I to S. The shortest distance from I to S. And the wave passes by, and then it hits J and goes on at time d. So this is dis. And it leaves this edge, or goes past this edge, at time d of js. Okay, and the difference of these two, this minus this, in absolute value, is at most vi minus vj squared by triangle inequality. Okay, because these squared values satisfy triangle inequality. Okay, so therefore, the amount of time, if you think of this wavefront that's sweeping by, the amount of time this wavefront is cutting the edge is the difference between these two, which is at most this. Okay, so if you integrate over all time steps, the amount of edges that are being seen at each step is this much, and you're integrating over this amount of time because the separation between S and T is delta. Therefore, this thing is upper bounded by the sum over all the edges of this value, which is, of course, the SDP value. Any questions about that? Okay. And so, yeah, you just simplify and you get that the number of edges in the minimum cut, the smallest cut, is at most the SDP value divided by delta, which is square root log n times the SDP value. Okay? All right. So this can be used for other square root log n approximations, a similar idea. And it turns out that what's going on here, what you're seeing on this page, this breadth first search over this new metric, this weird metric, is something reminiscent of the region going argument of Leighton Rao. And there are analogs of this for other problems which have been done. For instance, for MIN-2-CNF deletion and several graph deletion problems by Agarwal, Charikar, Makarichev, and the Makarichev brothers are in the audience here. Min-linear arrangement by Charikar, Karloff, and Rao. Non-uniform SPARSEST CUT in joint work with James Lee and Asaf Nahor. Min ratio vertex separator and balanced vertex separators by Feige, Haji Agai, and James Lee. And they use the structure theorem plus other ideas. So let me give you just a very quick introduction to how they do it. So for instance, in the paper of Agarwal, Charikar, and Makarichev's, they prove a modified structure theorem where there's some directed version of an L2 square metric, whatever that means. And there's a weight function on the nodes. So remember, in the structure theorem, you find two sets S and T, where each of them contains a constant fraction of the vertices. So here they contain a constant fraction of the weight. Okay, so there's a weight function on the nodes, and G is some graph. And what you prove is that there exists a subset S that contains a tenth of the total weight, and such that the distance associated with all the edges leaving the set is at most square root log n times the distance over all the edges. Okay, so this is something very similar to a technique introduced by Leighton and Rao called the region growing idea, except here they had log n instead of square root log n. Okay, and that's what this new geometric stuff gives you. Okay, so and then some of the other papers have more complicated things going on. Okay, so that was my second part, the new approximation algorithms via semi-definite programming. And now I want to talk about geometric embeddings of metric spaces. And let me start by defining what a geometric embedding is. So suppose you have a finite metric space. where you have a distance function d, which assigns a distance to each pair of nodes, between each pair of nodes. Okay, it satisfies triangle equality. So geometric embedding is just a mapping that maps each node to a point in the geometric space. Let's say we are trying to embed into the Euclidean space. And so each x and y maps to some fx and fy. And the distortion is the minimum c, the minimum quantity c, such that for every x, y in your space, the distance in the target space is sandwiched between the original distance and c times the original distance. So that's the distortion of the embedding. And there's a lovely result of Bourgain which says that every endpoint metric space embeds into L2 and actually in many other norm spaces with distortion log n. Okay, so as I already mentioned, Lineal, London, and Rabinovich brought this result to our field in some sense. And they gave an efficient algorithm to realize this map. So Bourgain's algorithm was exponential time. But they gave an efficient algorithm and then pointed out that you can use this in all these algorithmic settings. And they also proved that the log n ratio cannot be improved in general. Okay, so this result is tight. Okay, so that's for general metric spaces. And that left open the question, can you improve that log n if x has some structure on it? For instance, if x is L1. Okay, these are endpoints with L1 distances defined on them, or L2 square, the thing we already encountered. And then does it embed into, say, L2 with better distortion than log n? Okay, that was just a question in just mathematics, which people were interested in. Okay, so so now let me say a little bit more about this connection between embeddings and cuts, and recall this cut semi-metric. Okay, a metric where all distances are 0, 1, and the ones correspond to being on opposite sides of the cut, and 0 on the same side of the cut. So there's a simple fact that a metric xd embeds isometrically in L1. In other words, those distances can be realized as L1 distances, if and only if it can be written as a positive combination of cut semi-metrics. Okay? So it's basically a positive combination of cuts. Okay, so what this means, it requires a little thought to see this, that if you can embed L2 square into L1, then, well, L2 square vectors correspond to solutions to SDPs, to families of SDPs, and L1 corresponds to combinations of cuts. And somehow, if you can do this embedding with low distortion, then you can get cuts from the SDP solution, okay, whose value is low compared to the value of the SDP. Okay. All right. So that's why it was interesting to embed, say, L2 square into L1 with low distortion. Okay, because then you could get some of these algorithms.
This L1 might as well be Bourgain high.
Yeah, that's actually just another way to state the same thing.
Yeah, not true, but so.
Yeah, it's not a complete Bourgain.
No,
into that's basically the same fact. Yeah. Okay. So here's the status report of this area. So I already mentioned that L1 and L2 are subcases of L2 square, this funny metric I introduced, and L2, it turns out, is a subcase of L1. So the question was, how well can you embed this into that and this into that? So what's the distortion you need? So the best lower bound for the first problem, L1 into L2, was square root log n. Okay, and also for the last one. So for embeddings into L2, the best lower bound was square root log n from 1969. And L2 square into L1, I don't think this was studied too much by mathematicians. It only became interesting after the Lineal Rabinovich paper, and then even there it wasn't known if there's a super constant gap. And recently, Koth and Vishnoi showed that actually there is a super constant distortion. That this does require super constant distortion. Okay, so this disproved the conjecture of Gomans and Lineal. who had conjectured that it was a constant, that you can embed these constant distortion, which would have been a great thing if it had been true, but turns out it's not true. And it uses Fourier techniques developed for PCBs, and I'll say in a minute why that arises. But anyway, it's a nice application of things that have been developed in another area of theoretical computer science.
Does it rely on the fact that P is different than NP?
No. It relies on kind of stuff you do. You have the Fourier stuff. Okay. So those were the lower bounds. So best upper bound. So until recently, the best was the Bourgain result, log n. Then using the ARV structure theorem and another thing which I'll mention in a second, Chawla, Gupta, and Rake came up with a upper bound of log into the 3/4. Okay, and remember that the lower bound is square root log n. So you do require distortion square root log n, and they showed that you could do better than log n, namely log into the 3/4. And then recently, with James Lee and Asaf Naor, we have shown that you only require distortion square root log n times log n. So almost as good as the lower bound. And okay, so that's the status report.
So
yeah,
those upper bounds apply. Those are each individual, or the brace is for all?
It applies to all of them. Yeah.
Oh, okay.
Basically, the upper bounds, the only thing we know is how to embed into L2. And so once you embed into L2, it follows that you can embed. If you can embed this into L2, then you embed this into L1. Okay, so that's the report of embeddings. Okay, so just wanted to just say in one slide why these structure theorems are useful in embedding upper bounds. Okay, so in other words, in constructing embeddings. And there's basically one essential idea that all embeddings seem to use, which is this recipe due to Fréchet. Because in general, it's hard to imagine how you embed metric spaces into a geometric space. So here's Fréchet's embedding. So you pick k suitable subsets, A1 through AK. So if you're trying to embed into k-dimensional Euclidean space, you pick k suitable subsets, A1 through AK. And this is where the magic occurs, what's suitable. And then you map x, some point x in the metric space, to this vector, the distance of x to A1, namely the minimum distance from x to any point in A1, x to A2, and so on. So that's a k-dimensional vector, and you map x there. Okay, so this is how you produce something geometric out of something non-geometric, namely a metric space. And by the triangle quality on the metric space, each coordinate also is at most for any points x and y. Each coordinate is at most dxy. Okay, so this map is after scaling is 1 Lipschitz. Okay, so why is the structure theorem useful? So the rough idea is that if you take the set S that's obtained from the structure theorem, okay, this guy, well, so then we know. Okay, so you try to construct so if you just look at the one-dimensional analog, so this thing. So you're trying to, so everything in A maps to 0, right? Because everything that's in A1 maps to 0. And everybody else maps wherever, the distance from A1. So if your distance was large, you want to map far away. Okay, that's what a faithful reproduction of the metric space would do. Okay, intuitively. So for A1, let's say you use the set S that you get out of the structure theorem. Well, then in the structure theorem, we know that for S, there's a set of points T which are far from S. Okay, and so somehow they map far from S. Okay, so on average, it's kind of doing the right thing. Okay, that's a rough idea. That's why it's these kinds of things are useful. But to actually formalize it, you need something called the measured descent technique of Krautskammer, Lee, Naur, and Mendel, which is a beautiful paper. And then that really shows you, how it formalizes what kinds of things you need here. And turns out the structure theorem can give you that. And then, you have to do a lot more work to actually come up with, the precise AIs. Okay.
Is there Any results saying how well this recipe can be in general? I mean, are there always
is it universal or not?
Is it universal?
So I think you have a paper, right? There's a counterexample.
How bad?
So you lose a log n to some power.
Log n to the epsilon.
Yeah, but this power is probably 1/2.
Okay.
Something, I don't, or 1/2 minus something arbitrarily small.
Yeah. So Fresher's embedding is not universal.
Yeah.
Fresher's, but it usually works for most things. Okay, so.
So there are things that embed isometrically, but any Fresher embedding, no matter what subsets you choose and which coefficients you put on these distances, you will lose a factor in square root of log.
Okay. Now I want to tell you in this one slide some idea of why Ehud's work is important for embedding lower bounds. So all right. So what Coates and Vishnoi do is they describe an explicit unit L2 square space, which requires distortion something like log 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 n. Maybe it can be only 2 logs into L1. Okay. And as I mentioned, that this was conjectured that sort of conjectured by Gomes and Lineal that that every such space actually requires only constant distortion. Okay, so this was a disproof of that conjecture. Now, remember that L1 has this nice characterization, so you're showing that this thing does not look like that. Now, L1, remember, has this characterization in terms of cut metrics. Okay, so L1 is all about cuts. So somehow you want some space X where you have a very good handle on cuts. You can reason about what its cuts look like. I mean, this is very handy. L1 is all about cuts, so you need some kind of space where you can reason about its cuts. So you need some kind of graph where you have excellent theorems about its cut structure. What its cuts look like, what near optimal cuts look like, everything. And the space is the hypercube. Okay, and so these guys indeed use the hypercube as a building block. It's used, in some rotated ways and so on, but it's the hypercube. And the observation is that, why does Ehud's work come into play? Well, a cut on a hypercube is a Boolean function. Okay, so 0 and 1. One side is 0, the other side is 1. So it's a Boolean function. And the number of cut edges is what's called the average sensitivity of the cut, of the Boolean function. Okay, so actually once I saw this in the Coates-Vishnoi paper, I said, yeah, this is what I knew about all these Fourier analysis results, and they all talk about average sensitivity, and what these guys say is, well, average sensitivity is just the cuts. So these are all these Fourier transform results that you know of, Kahn-Lineal, Prietz-Bloch, Hassad, Bourgain, etc. These are theorems about cuts. They are isoparametric theorems. Okay, so they use all those theorems to prove that the space that they construct, which uses some kind of noisy hypercubes, require a non-constant distortion into L1. Okay, and this has been improved by Coates and Naur to give lower bounds for embedding earth mover and edit metrics into L1. So in general, we were lacking techniques for proving that things don't embed into L1. And then this paper suddenly introduces these ideas, which I think will have even more application. Okay, so now we are talking about expander flows and n-square time algorithms. Just want to describe in a couple of slides what are expander flows. Okay, so here's the motivation. So think about an approximation algorithm. For one of these cut problems, it gives you a cut, and it's near optimal. It claims it's near optimal. Okay, so in other words, it's at most of some small factor times the best cut. Okay, so implicitly, any approximation algorithm must certify that the cut, the best cut is at most something, right? And now if you think about it, that's a co-NP problem, right? That's a co-NP statement, that every cut is at most something, okay? So it seems like there should be no short certificate, right? So somehow any approximation algorithm must give you something, a certificate for a co-NP problem. Okay, so that's the sort of.
No, it's at least. At least.
Did I say at least? Oh, sorry, at least. I'm sorry.
Yeah.
I meant at least. I'm sorry. I saw some puzzle words. Okay, so again, to restate that, so every approximation algorithm is implicitly telling you that the best cut is at least something, and that's a co-NP statement. Okay, that every cut has a lot of edges or some amount of edges. Okay, and that's a co-NP statement. And so just imagine, you're okay. So it turns out these algorithms do give, by duality, they give some kind of certificate. That's trivial, by STP duality. But turns out there's a certificate with a very nice description, okay, which gives you some structural insight into what expansion is and how it arises. Okay, and that's what expander flows are. Okay, so let me introduce them as follows. So suppose you have a graph and you're trying to convince your friend that every cut has some prescribed number of edges. Okay, some agreed upon quantity. You're trying to convince your friend that every cut has that many edges. So as I said, that's a co-NP statement. Okay, every cut has some number of edges. So that's what you're trying to prove to your friend. And that seems hard to do, okay, to give some kind of succinct certificate. So here's an idea. You embed a deregular weighted graph in your host graph such that for every cut S complement, the amount of weight going in this weighted graph is at least d times S. D is the degree, so the amount of weight incident to S is just d times S, and a constant fraction of that is going up. Okay? And what do I mean by embedding? It means that you route these edges along paths, and you have congestion 1. Okay? All right. So what this is proving to your friend is that in every cut there must be a lot of edges because all this weight is going across. Think of it as a flow. It's flowing on, think of it as liquid flowing. It's going through these pipes, so there must be a fair amount of volume, pipe volume, right, in each cut. Okay, because a lot of liquid is flowing across the cut. Okay, so suppose that's what you try to do. Now you might say, wait, that's a circularity, right? Circular reasoning. Because this is exactly the problem I started with. I'm trying to prove that in some graph, every cut has a lot of edges. And now you're embedding some other graph, and now trying to prove that that graph has, the same thing, right? Something similar. Well, the reason it's not a circularity is that the graph you start with is arbitrary, whereas this graph that you're embedding is totally under your control. Okay? And so in particular, you're free to pick as nice a graph as you like. And also such graphs, so I already said this, it certifies that the expansion is omega d. And such graphs are expanders. Okay? So there are various notions of expanders. I'm talking about an edge expander. The amount of weight incident to each side to the side S of the cut is d times S, and a constant fraction of it is crossing the cut. That's what's called an edge expander. And those can be certified. In those graphs, you can, by computing the eigenvalue, certify that the expansion is a constant. And so that's what breaks the circularity. Okay, so you're embedding an expander, and you just tell your friend, compute the eigenvalue, and the eigenvalue will be a constant, which proves that my graph is an expander. Okay, and so the theorem that we proved with Vazirani was that if G has expansion alpha, then it has a deregular expander flow in it, where D is alpha over root log n. So you can certify that the expansion is at least alpha over root log n. Okay, so it gives you some insight into how expansion arises. Okay, the graph contains an expander in it. Okay, and then the faster algorithms for computing the cut actually use this fact. They compute a flow and eigenvalues, and all of those can be done very fast, and you can do it in n squared time. Okay, a quick example of expander flow. A bad example of a graph for like the spectral technique is a cycle, n cycle. So let me show you how our algorithm gets across it, gets around it. So yn cycle is not bad for it, because you can embed an expander in it. Okay, take any three regular expander, Gabriel or something, and put a appropriate weight on each edge, and you can embed it. Okay, so we show you how to embed this. In general, you wouldn't use Gabriel, you would use some arbitrary expander, and you would compute it by some flow computation. Yeah.
Can you say again what you mean by embed?
Okay, so it's a multi-quantity flow. Okay, so each edge has capacity 1. That's it.
So what do you mean when you say embed this graph?
Embed just means it's the flow can be routed. So between I and j, if there's an edge in the expander, that's like a unit of flow or some appropriate
Maybe it's worth saying that Leighton Rao is really embedding a complete graph.
That's right. Yeah, I had it on the slide, the previous slide, but I didn't say it. Leighton Rao and Jerome Sinclair, the canonical path technique and the Leighton Rao technique, was a special case of this where they were embedding the complete graph. Okay, and this was actually the starting point of our work, to try to embed and expand it. Okay, all right. So I really don't. I should be stopping, right? Is it?
Do you want to give us open problems or haven't done that? It looks like you've done that.
And so I'll skip this then. Okay, I was going to. I won't have time for this. I can do it for people who want to stay. This was an outline of the proof of the structure theorem. Oh, okay. Open problems. So it's still an open problem whether you can improve the approximation factor of square root log n. As I mentioned for general SPARSEST CUT. So I forgot to mention this. This coefficient result, the distortion required to embed L2 square into L1. It's an interesting result that quantity, the distortion required there, is exactly equivalent to the integrality gap of the corresponding semi-definite program. Okay, so it's a connection between something purely algorithmic and purely mathematical, purely structural. And so the coefficient result also implies some log n lower bound on for general SPARSEST CUT, but for edge expansion or the other problems that I talked about, we don't know. Okay, so there's an integrality gap, which is for sure, which is unconditional. And then the PCP type lower bound uses the unique games conjecture. But for uniform SPARSEST CUT, edge expansion, some of the other problems, 2-CNF deletion, many of those things, we don't have any lower bound, even assuming unique games. So as far as we know, there could be a constant factor approximation. And yeah, Asaf and I seem to agree that there should be a better algorithm. But maybe we'll wait another decade for it, who knows. Better distortion bound for embedding L2 square into L1. As I said, that's very related. But it's possible that there could be a lower bound. Again, there's a gap, but that would just prove that the current SDP we have will not do the job, even if you improve the lower bound. But there could be other algorithms. The third thing is to remove the need for solving semi-definite programs, because even though they take polynomial time, that's like n to the 4, n to the 5 time, and that's not really practical. And I mentioned that there's an n squared time algorithm for SPARSEST CUT now using expander flows, but it would be nice to come up with similar fast algorithms for other problems. And even for SPARSEST CUT, we have a heuristic which we suspect may run in m log n time or m polylog n time, what Christian asked about. And somebody at Yahoo actually implemented something like that, and actually it does very well, better than spectral methods. For general graphs, spectral methods do well for like planar graphs and stuff, but for general graphs, this heuristic seems to do better. It's some stripped down. He implemented a very stripped down version of the heuristic. So that's the other problem, order m. I don't mean literally order m log n or something, instead of n square. And as I said, the Yahoo experiments seem to suggest that the heuristic may actually do it. And other applications of expander flows. So, for instance, now Rabbani and Sinclair have already applied that notion to prove some purely mathematical results about Banach spaces. So, but I think in general, that structural characterization of expansion, even though it's approximate, should have other applications. And that would be nice. Thank you.
By the way, there are 2 more theory talks this week. Mike Sachs is speaking on Thursday, and Remy Monison is speaking on Friday.